Okay. It's my great pleasure and honor to introduce our last speaker this morning session. Alberto Barofsky is one of the most distinguished mathematicians in Latin America. He has contributed to the development of dynamical systems, geometry, and topology in the region. Alberto studied mathematics here at the Facultad de Ciencias. Later on, he was a student of Solomon Lefschetz and Mauricio Peixoto. After a stay at IMPA in Brazil, he concluded his PhD in 1973 at the University of Bonn. Back in Mexico, he was first a researcher of the Centro de Investigación y de Estudios Avanzados, CIMBESTAB, where he stayed until 1987, when he left to Italy to coordinate the area of mathematics of the ICTP in Trieste, the International Center of Theoretical Physics. There, he worked to disseminate mathematics in Latin America and contributed to strengthen relationships among mathematicians from all over the world. He entered the University of Lille in France as professeur de première classe. There he established a high-level research group in geometry and dynamical systems. Finally, in 1998, he established his permanent residence in Mexico as researcher at the Instituto de Matemáticas in Cuernavaca. He's a warm and generous colleague with whom one can discuss about any mathematical topic. Once, Dennis Sullivan wrote, "In the arc of mathematical animation and inspiration, Alberto Verjovsky is not only the best example alive today, but possibly the best there ever has been or the best there ever will be." Let's welcome Alberto.
Thank you very much. Thank you. Well, those last words are from Dennis Sullivan, who is my very, very good friend, and I appreciate that. And it's a pleasure for me to be here, my alma mater, and to be part of this celebration. I thank the organizers for having invited me. So the title of my talk is Compact Three-Dimensional Geometric Solenoidal Manifolds, and this is a work in progress with Dennis Sullivan. So a k-dimensional solenoidal manifold, or also called lamination, or transversal decanter-foliation, there are several synonyms, is a metric space which is locally modeled on the product of an Euclidean k-disk and an infinite, perfect, and totally disconnected set, which is those sets are subsets of the Cantor set. Solenoidal manifolds appear naturally in many, many branches of mathematics. Sounds like something very esoteric, but actually it's very common. And in this talk, we will be mostly concerned with compact lamination, such that the transverse structure is a complete Cantor set, and not just a totally disconnected set, a complete Cantor set. And so let's see some examples and why I say it's in topology, independently Vietoris and Van Danzig discovered the famous dyadic solenoid. And it's one of the fundamental examples in topology. I know here in the Facultad, in the Institute and the Facultad, there are many people that work in topology. And the development of homology and cohomology theories, which could be applied to these spaces, which are very, for instance, in the famous paper by Steenrod, regular cycles of compact metric spaces, which appears in this lecture notes in topology, University of Michigan. It's accessible now in the internet. It's a beautiful paper where many things are described, in particular Stiefel-Whitney classes. And like yesterday we were talking about the book of Milnor, so it's a very good read. And this is let me describe this dyadic solenoid. So you take a solid torus. Here's the yellow one. And inside you embed thinner, this is a half thinner solenoid and longer, and you wrap it twice around. So you have one solid toroid inside another one. And now inside the green one, you will embed a solid toroid which is 1/4 thinner and 4 times longer, and you will wrap it around, and you keep going like that, and then you will take a nested sequence of solid toroid. And well, here's a better picture taken from the internet. And this is what, at the end, what you get will be a topological space that's fibers over the circle with fiber of the Cantor set. Actually, the fiber can be canonically identified with the dyadic integers, the units in the dyadic field. And it's actually fibers over the circle are the monodromy. So if you see this previous picture, if you cut this torus with a transverse, you get a disk, and then the yellow, the green torus will meet in two disks, etc. So you can describe this as you can codify this by the dyadic integers, and if you move the disk and turn around one turn, you have what is called the monodromy of this fiber bundle, and this is actually the adding machine, adding one, and it's a translation. So this is a compact abelian group, the dyadic numbers. It's a compact abelian group, and this has a minimal translation, much like the irrational rotation in the circle. And that means that all the orbits, it will foliate or laminate this object into lines which are embedded densely in this object. And that's the reason it's called solenoid. I mean, now when you open your car, you don't see it, you have to take it to the agency, but before they have solenoids, you know, the bobbin. And so that's what this is named. So this is so it appears in topology, but actually they are the Pontryagin duals of discrete locally compact Hausdorff abelian groups. The Pontryagin dual of a discrete group is the set of mappings from that group into the unit circle, and this forms for a discrete group. The Pontryagin dual is a compact group, and well, if you take now the additive group of rationals, and you take the Pontryagin dual, this is a solenoid. It's the universal solenoid, one-dimensional solenoid, which is very much like the one I presented before, except you do the following. You take the solid torus, you take the one thinner one, wrap it 2 times, then inside wrap it 6 times, then you go through the factorial, no? 2 factorial, 3 factorial, 4 factorial, etc. And if you take this nested intersection, now you have a Cantor topological space that fibers of the circle with fiber, the profinite completion of the integers, namely is the product of is the Cartesian product of P ZP, where ZP are the p-adic integers, which is always a Cantor set. So it's a product of Cantor sets, countable product of Cantor sets. Cantor sets here, we recall that a Cantor set is topologically characterized by being a compact set, which is perfect and totally disconnect topological. And so that means that it's very, for instance, the dyadic solenoid is the Pontryagin dual of the dyadic rationals. And so it's interesting. Well, also solenoids appear as basic sets of Smale's diffeomorphisms, which are very generic. And in particular, one-dimensional attractors are examples of solenoids, and they were very studied by Bob Williams. Well, they also appear as a Julia sets of polynomial Henon maps. These are polynomial maps from C2. And if you iterate them, you know, like all those beautiful pictures of the Mandel-Rosette or Julia, you can look at Professor Milner's book. But this in 2 dimensions, you iterate, and surprisingly, you get to the 2-dimensional solenoids. So they will be modeled on the complex disk. There are solenoids whose leaves are copies of essentially C, embedded in 2-dimensional. And also, essential lamination has played a very fundamental role in the study of 3 manifolds, for instance, as witnessed by the deep theorems obtained by David Gavai, who gave a talk here. And but there's a canonical, so a very important character in this talk is K. K will denote the Cantor set, and H of K is another very important character in this my talk. H of K is the group of homeomorphisms for the Cantor set. And there's a canonical way to get, so essentially I will be talking, a prototype solenoidal manifold will be the following, will be a manifold and a Cantor set vibration over this manifold. And therefore, many times, the Cantor set is a group. Actually, if you take a finite completion of the Cantor set has the structure of a billion or non-abelian group in many ways. And so therefore, I will be talking essentially of principal bundles over manifolds whose fiber is the Cantor set. So the Cantor set, we shouldn't understand, just because it's totally disconnected, take it away from the list of principal bundles. In fact, there's a whole part of the book by Steele speaking of that. So one canonical way to do it, to construct from a manifold, a solenoidal manifold, is the following. Take a manifold, take a compact manifold N, and take rho, a representation of the fundamental group, into the group of homeomorphisms of the Cantor set. So this is the group, fundamental group, and this is the group of homeomorphisms. And you take a homomorphism from there. And then there's a lamination called the suspension rho. It's like more or less like the Borel construction, if you want, which is obtained by taking the quotient. So you do the following. You take the universal cover of N, multiplied by the Cantor set, and now you will let the fundamental group act the following way. In the first, in N acts just exactly by deck transformations. And in the second, in the Cantor parameter, well, you take via the representation, you take rho, this rho of gamma is a homomorphism of the Cantor set, so you can apply it. And you can easily see that this is a free, proper action, like Professor Milner talked in the first lecture of this conference. And if you take the quotient, so it acts free, properly, and totally discontinuous. Therefore, you can take the quotient. It's a beautiful Hausdorff space. It's actually a fiber bundle, Cantor fiber bundle over N. And this is a canonical way to obtain thousands of laminations via representations of the manifold. Now, here's Dennis Sullivan has shown, together maybe with Bob Edwards, but I think all by himself, has shown the following beautiful theorem. It's not surprising, but it's pretty. You take any compact-oriented one-dimensional solenoidal manifold S. Oriented means that you can give an orientation to the, so it locally looks like the integral times the Cantor set. And now, this has a global, this looks like a flow, right? Looks like the orbits of a flow. And then theorem says that there's a global cross-section. You do this more or less intuitively because you have local cross-sections, you have Cantor sets, and you can paste them very beautiful. And the theorem of Dennis Sullivan says the following, says there's a Cantor set transverse to the leaves, so that there's a first return map, and it looks essentially the mapping torus of a homeomorphism of the Cantor set. So any one-dimensional oriented solenoidal manifold is obtained by taking the Cantor set, multiplying by an interval, and gluing the left with the right by a homeomorphism. And that's the way you obtain everyone. Now this beautiful observation, which you can do by Thornton, it has been shown by Anderson a long time ago that the group of homeomorphisms of the Cantor set is actually a simple group, doesn't have non-trivial normal subgroups. In particular, it's equal to its own commutator, which means that every homeomorphism of the Cantor set can be expressed as the product of G commutators. And now you take a surface of genus G, dig a hole, take a hole, an open disk, and the fundamental group of the complement is the free group with two G generators, and you can represent F. Suppose that F is a homeomorphism. So you have a one-dimensional solenoid is a suspension of a homomorphism F. Now express this F as a product of two G commutators, and give a representation of the fundamental group of the surface. No? And what you have is that, so you have commutator K1, H1, K2, H2, Hk, Kj. So what you have is, by the previous construction, you have a Cantor bundle vibration of the puncture surface, such that in the circle boundary is F, which means it's beautiful, means any one-dimensional oriented solenoid is coordinate to 0. It's beautiful. So it means there exists a compact lamination with boundary. The definition of lamination with boundary has an obvious definition. And therefore, that's one example of. But what I want to talk, my main talk here is geometric three-dimensional solenoids. So will we be concerned with compact laminations? Model on the, you see there's beautiful fact in three-dimensional topology that there are 8 geometries that appear so the structures on a three-dimensional complex manifold. So this is the definition, locally homogeneous manifold. So are manifolds that are locally modeled on E3, and the coordinate changes are translations in this. Also can be modeled in the real line, can be modeled in the sphere, can be modeled in hyperbolic space. So in the list of 8 geometries, so what we have, this is the definition I give. A compact three-dimensional geometric solenoidal lamination model on a Thurston model. So there are 8 models. Briefly, a geometric solenoidal three-manifold, model of Verjovsky, consists of a compact metrizable space M together with a family of charts such that, first of all, they cover the manifold. Then they can be described as a product of a Cantor set times an open set. And this is the important thing. The coordinate changes are translations in the model. So are either hyperbolic isometries, Euclidean isometries, rotations, translations in SL3R, in all the 8 models. And that means in that way each well, I should have given this one before. Well, I gave the definition of a solenoidal manifold, and now if you take a disk contained in a chart, so the chart is a disk cross K. This disk, you take the maximal connected component of that, and that's called a leaf, exactly like foliations. And that means that the leaves of a lamination are manifolds. Another thing, you can make the change of coordinates in such a way that the leaves become differentiable manifolds. And that means, and vary continuously on the Cantor direction. So this means that we are consider laminations as a generalization of a, so you can do all the things you do in differential geometry longitudinally in a leaf-wise. So that you can speak of Riemannian metric, leaf-wise Riemannian metric, leaf-wise differential forms, leaf-wise complex structures, etc. And what I'm talking here in the previous is you can think of a leaf-wise geometric structure. And that's what, see. And so, you know, a lamination is something that very much wants to be a manifold. In fact, Dennis Sullivan calls them a diffuse manifold. You see, if you're a little blind, you take your glasses, you might think that lamination is actually a compact leaf, no? And then you take a better graduation glasses and you see more leaves, and then on defining, wow, you see a Cantor set. So I like to think that it's a manifold that actually, I just got operated of the cataracts. That's what it makes me very happy to talk about that. So essentially, it's doing Cantor set things on the transverse direction and differential geometry, differential topology, complex geometry along the leaves. That's the game. No? Okay. Well, in this previous geometric lamination, the leaves are immersed in dimensional manifolds with a geometric structure modeled on the geometric Thurston model. And this is what I just said. On a smooth lamination, it makes sense to speak of a smooth structural lamination. It means continuous on the Cantor direction, smooth in the leaf direction, and you can do everything, you know. I have to repeat, everybody heard the following thing that I always, it's the third time I repeat it, but I heard that when Professor Spencer, the one of the formation theory, Cordaido Spencer, was asked what a sheaf was, his answer was very easy. It's topology this way, algebra this way. And with that, I thought I understood what a sheaf was. Actually, it's false. And so what I'm talking about is manifolds this way, Cantor groups this way. So this is summarizes my talk in a few words, but then you have to do something. No? Okay, so you can do the ramp theorem, laminatic. So let me tell you, it's not here, but let me tell you a theorem. So it makes sense to speak of a two-dimensional smooth lamination. It's a lamination by surfaces, okay? Now take a compact lamination by surfaces. Now take a laminated Riemannian metric. So it induces on each leaf a Riemannian metric. And now there's a fundamental fact that every leaf knows its type. So every leaf has a metric, and there's a famous theorem by uniformization theorem saying that given any Riemannian metric on a surface, connected surface, compact or no, there's a fact that you can multiply this metric by a smooth function in order to render this metric of constant curvature -1, 1, or 0. And you can speak of a Euclidean metric, elliptic metric, or hyperbolic metric. So in a compact lamination, you can speak without ambiguity of a hyperbolic lamination. This is independent of the ambient metric you give, because two metrics vary in a bounded fashion. So it makes perfectly sense to speak of a hyperbolic lamination. Every leaf is conformally equivalent, its universal covering is uniformly equivalent to the hyperbolic Poincaré disk. And there's so to emphasize the fact that you can do differential geometry in the leafwise direction, there's a theorem that was proven by Alberto Candel and myself independently, saying, theorem, if all the leaves are hyperbolic, there's a continuous Riemannian metric, which is C infinity on each leaf, which renders this leaf C infinity. In fact, now, think about it, since I say that you can do everything in differential geometry or differential topology, you can foliate it, a foliated version. What about taking a three-dimensional lamination, taking a metric, and let the laminated Ricci flow? That makes sense. And you let it flow, and maybe for the case of surfaces, you start from a Riemannian metric, you take the Ricci flow, two-dimensional Ricci flow, let it flow, and it converges to the uniformity. So I'm actually, well, now that I almost have a proof of that, but I still have some difficulties. But so you can maybe take a three-dimensional manifold, take the Ricci flow, and prove some sort of geometrization version of that. Could be possible to do it. So a lamination is said to be minimal if all the leaves are dense. Then you have the notion of holonomy invariant. It's an assignation of an invariant metric to which transverse, which is invariant on the holonomy, but I won't use it. Now, this is the most fundamental example. So you take M, a compact geometric manifold, model on one of the models, except this one. You see, this model is simply connected. I don't want that one. So since the fundamental group of M, so this is a compact manifold, not a lamination, just a compact manifold. Well, since the fundamental group of M is infinite and residually finite, yesterday was given the definition by José Antonio de la Peña, is residually finite if the intersection of all normal subgroup is trivial, or else if given each element different from 0 is not contained in a normal subgroup of finite index, then you can consider the following. This is the fundamental object in this talk. You take the tower of all its finite pointed covers. So you take, and that can be done for any manifold, any, let's say, smooth manifold, compact smooth manifold whose fundamental group is residually finite. You take your manifold, fix a point, and take all the finite covers. The finite covers is a directed set because it corresponds to the subgroups of the subgroups of finite index of the fundamental. So think of this as a directed set of finite covers. And now a canonical thing to do is to take the inverse limit of that, and you take a point. A finite cover has a finite number of preimages, etc. So what you have actually as fiber is a Cantor set. So this inverse limit is a Cantor set. It's a canonical way, given a manifold with a residually finite fundamental group. It's a canonical way to have a lamination. But actually, you see, instead of taking the coverings corresponding to surplus of finite index, you take the covers, because a finite cover corresponds to a finite index, surplus of the fundamental group. You can take actually surplus of finite index, which are normal, and so you take the tower. Now each fiber is a finite group, the group of deck transformations, because the covering is a Galois covering or regular covering. That means that if you take the infinite tower, what you get is a Cantor bundle over the manifold, and this is a principal bundle where the group is a Cantor group. The Cantor group is called the profinite completion of the fundamental group, and this actually you put in one capsule all the ingredients of the fundamental group. So here's what I say. You take the inverse limits of all coverings, and you could think actually, so this is what I told you, written, take all the fundamental, all the finite cover, and you can take the, in fact, you can even do more, take all characteristic subgroups. So subgroups which are invariant on their isomorphism of the group, not only normal subgroups. And then you take the inverse limit, and that way you have that. So in fact, M is called the universal covering of M. So let's think a little bit. So a finite cover, I mean the fancy definition, the pedantic definition of a covering, of a regular covering, is a principal bundle with fiber, a discrete group. Now the fancy definition of covering, not necessarily regular, is a homogeneous fiber bundle with fiber is discrete. Now, all this thing I'm talking about is replace discrete by totally disconnected, by Cantor set. So in our head, we think of this as generalization of a covering. No, it's like a Cantor covering. That's what I want to convey, this idea. And this object, therefore, in one single object, M bar, it contains all the algebraic and geometric ingredients of the fundamental group of a manifold. And well, here's just the same thing. You have a group, and this group is so this Km is the inverse limits of these deck transformations. So it's a Cantor group, because an inverse limits of finite groups of increasing order. And this is called the fundamental group of. This is an idea that Grothendieck very much likes, because he takes an algebraic manifold and takes all étale coverings, all finite étale coverings. Don't take one covering. Take all finite coverings at once and put them in a box called the inverse limit. Okay, so that's what it is. And well, now what happens here is the following: is that because the group is residually finite, every leaf will be simply connected. Every loop unwraps in some coverage because residually finite. And therefore, the leaves of this universal covering will be copies of the model. For instance, example, we will clarify everything. Take a compact hyperbolic 3 manifold and take the tower of its finite covers, finite Galois covers. And that will be a lamination or a solenoidal manifold, such that every leaf is an embedded, densely embedded copy of H3, hyperbolic 3 space. And so that's what one example. Well, now, so we have a principal fiber bundle over the manifold. The fiber is the profinite completion of a fundamental group. And because it's a principal bundle, this lamination is topologically homogeneous. Namely, you can pass from one point from another by a homeomorphism. Well, you can do this on the fiber because it's a homogeneous fiber bundle, and therefore the groups act transitively. So you can change one point from the fiber to any other. And then if one leaf cuts the fiber in the same point, well, you can go from one to the other by a simple move. So these solenoidal manifolds have the property that are topologically homogeneous. And the reciprocal construction is valid, and via the representation. And this is the important definition that I want to. Two compact three-dimensional manifolds are commensurable if there exists a common finite cover. So there's M3 that covers M1 and covers M2. And this is an equivalence relation, the relation of commensurability. Okay? And one important problem in three-dimensional topology is to characterize the commensurability classes of manifolds, hyperbolic manifolds. Oh, okay. This is what I want to use this. Suppose M1 and M2 are commensurable. So they have a, you see, this tower of covariance has a beautiful property. Like you call it the Gardner property. It starts from one cover above and cut all the branches below. And take all the cover, start from there. And I claim if you start from there, it's the same thing I started from bottom, because there's a canonical homeomorphism, which is continue the path. It's like a shift map. And therefore, you can start from, here's a beautiful idea by Dennis Sullivan, is you take the surface of genus 2 and take the tower of all its finite coverings. Now, every surface of genus greater or equal than 2 covers the surface of genus 2. No? The surface of genus 2 covers nothing, but every surface covers the surface of genus 2. And therefore, you can start from the surface of genus 2 and take the tower of all its coverings, finite coverings, and then what you can do is take a covering up above, cut all the branches below, and start there. And that's a beautiful idea of Dennis Sullivan to construct a universal time-Miller space. But anyhow, if you have two manifolds which are commensurable, take the infinite tower of the first one, the infinite tower of the second one, and you can start from M3 for both. And that means that this profinite completion, any information you get, it will imply information on the commensurability class of manifolds, right? So that's what makes it interesting. This tower carries the information of all commensurability classes. Corollary, the commensurability classes of three-dimensional geometric manifolds are determined by the isometric classes of the solenoidal algebraic covariance spaces. And so this contains all the information of the commensurability class. And now we want to know when a solenoid is obtained by this process of taking inverse limits. And there's a beautiful theorem of McCord. It's a solenoidal manifold is called a McCord solenoidal manifold if it's obtained by as an infinite tower of coverings like the previous one. And there's a beautiful theorem by Clark and Stephen Horder. If sigma is a compact topologically homogeneous solenoidal manifold of any dimension, so it's then sigma is a McCord solenoidal manifold. In other words, it's obtained as an inverse limit of covariance of a manifold. And now, what I really want is the solid. If I'm thinking that solenoidal hyperbolic three-dimensional manifolds are like hyperbolic manifolds, what about problems like the Agel? You know, there's a recent theorem by Ian Agel solving a question of Bill Thornton. Bill Thornton had the following question: is take a hyperbolic manifold of dimension 3. Then there should exist a final cover so that this cover fibers over the circle. And that is because Thornton had proven before, it's important, had proven before the following fact. If you take a surface of genus greater or equal than 2 and take a homeomorphism, which is called pseudo-Anosov type, which is a definition is the following, is if you take any closed curve representing a geodesic and you apply F, the length of that, the length of the geodesic represented the iterates grows. That's the one definition. Another definition is that this surface contains two foliations called pseudo-Anosov foliations, which are transverse. One is expanded and the other is contracted, like the Anosov flow. And Thornton proved that you take one of these surfaces, multiply by an interval, and glue, take the mapping torus, that's a hyperbolic 3 manifold. And that means that we can actually have the theorem of Agel in a solenoidal version. Theorem. This is, of course, this is to say any hyperbolic manifold virtually fibers over S1. Virtually means probably the manifold itself doesn't fiber, but a final cover does fiber. So there's his theorem. Consider a compact hyperbolic solenoidal manifold is something which is modeled in H3 with this group acting. This is the group of isometries of H3. Suppose in addition that sigma 3 is topologically homogeneous and minimal. And every leaf is simply connected. Well, then there is a locally trivial smooth vibration. So this solenoidal manifold fibers over the circle, and the fiber is a two-dimensional solenoidal surface. And there are many fascinating questions, like what does it mean, for instance, for this Sullivan lamination that I told you, what does it mean to be pseudo-Anosov? What does it mean to have the theory of quadratic differentials? There is very fascinating problems. And so this, of course, a very beautiful theorem, except it relies freely from two deep theorems. So I claim only I put 2 and 2 together. It's on the deep theorem by Ian Agel, future vibration theorem, and the other deep theorem of characterization of McCord solenoidal manifolds as being topologically homogeneous. So you put 2 and 2 together, you get, but still a very interesting consequences of this, because of the following reason is, so you take a hyperbolic, you take a hyperbolic manifold, and don't start the tower of covariance there. You start from the one that fibers over the circle, from the Agel. Since you can start anywhere, you start here. These fibers over the circle. And therefore, you take the towers of covering of that, you will have a very beautiful structure, and you can study things like, well, many, many things. This is the proof. It's a complete direct application of just what I said in words. You start by the Ian Agel, so no. And this is the process of being understood. Okay, so well, forget about this. So this theorem can be generalized, is a laminated version of Ian Agel theorem. And why do I say this? Okay, so if you have two hyperbolic manifolds that are commensurable, Let's think a little bit about some invariants. For instance, take the set of all lengths of closed geodesics. So it's a bunch of numbers in the real line, maybe with multiplicity. This is a discrete set of the real lines. The simple geodesics is a discrete, and if they repeat the multiple covered geodesics, well, okay. If you have two manifolds, so take the set of geodesics of the first manifold of M1, of M2, and suppose they are commensurable. Then lift the geodesics to M3, which covers both. Suppose the covering is of order n. Then the length of the geodesics is multiplied by n. So this means that if you take this data, which is the list of all lengths of geodesics, and you multiply by the positive rational numbers, this is an invariant of the commensurability class. You see, the lengths of geodesics are multiplied for coverings or for projections are divided, and therefore it's a beautiful invariant. And I want to obtain all this work I'm doing is in progress, as I say, is in order to detect invariants of commensurability class of three-dimensional manifolds. So this is part of the. Okay, so the theorem therefore says that Sullivan constructed the universal solenoidal manifold, the set of coverings of the surface of genus 2, and every hyperbolic lamination is obtained from taking that one and a mapping torus of something that I don't know how to write, which will be called, when I discover it, a Pseudonosov diffeomorphism. And so essentially it means the commensurability class is completely determined by these objects. The profinite completion of the integers and the semidirect product with the profinite. So this contains all the commensurability invariant of the manifold. Okay. The laminations that Thornton obtains have something which is called a stretch factor. This Pseudonosov diffeomorphism has something that's called the stretch factor. It's the rate of dilation of one of the foliations. And if you take a covering, this stretch factor is raised to some power, and therefore, what I really want to do is commensurability invariance of compact hyperbolics. And this is the book in which I'm basing many of it's a beautiful book I highly recommend. It's a book by Alan Reed McLachlan. And these are very interesting. You see, you take a hyperbolic manifold, so it's H3 divided by discrete co-compact subgroup. So this is the group of isometries of H3. So this, and there's a relation between the trace of the elements and the length of geodesics. And so if you take the field generated by all the traces of all the squares of the elements, this is an invariant of the commensurability class. Okay? But my question is, what is the relation between the dilation of the Pseudonosov, which, by the way, this lambda dilation is a beautiful algebraic number. It's actually a Piperron number. It's a number that has the property that this number and all these Galois conjugates are in an annulus. I want to know what the relation between the field, the Q of that, and the geodesics of that. What is this? Well, we'll forget all that. What was that? Well, I gave a talk on the same talk, a little better, in another occasion, and Misha Kapovich was there, and he liked the theorem, and he was motivated to prove the following theorem. Let L be a compact solenoidal n-dimensional Riemannian lamination with leaves isometric to Hn. Suppose that the lamination is homogeneous, which means that the group of homomorphs act transitively on L. Then there exists a closed spherical in manifold M, such that the n is different from 4, because that's the Poincare conjecture of 4. Then M is hyperbolic, and if n is equal to 4, then M is homotopy equivalent. So it means that all of them is sort of like a geometrization theorem for lamination. It's a really beautiful theorem, and was motivated by that talk that I gave, so I'm very happy that at least, the real question that Dennis asked me is the following, is for the solvable case. So one of the most fascinating geometries by Thorson is the solvable case. The solvable case is the following. You take a torus, a flat torus, and take the suspension of a hyperbolic, so a flat torus is actually a abelian Lie group, compact abelian group, and you take an isomorphism, which is given by a matrix in SL2Z, A, B, C, D, and suppose that it's hyperbolic, namely trace is different from 2. And then you take the mapping torus of this map, and this is all solved manifolds are obtained this way. And so the question is, how can you determine the commensurability class of that? And I came to the solution using this, saying that there's a one-to-one correspondence between real quadratic fields and solved manifolds. I was very happy. I wrote to Dennis, but unfortunately, Walter Neumann had already proven that. But our proof is based in doing the following. You take this suspension and take the profinite completion of that. And therefore, what you have is something that will have as fiber the universal torus is the profinite completion of S1. The profinite completion of S1 is this solenoid, universal solenoid, one dimension. Multiply it by, and then take a mapping torus. So it's a matrix now in SL2 Z hat. And that conjugacy classes of those matrices equal to. So I give you, I think I'm finished here. And I'm sorry I skipped so many, but there are too many slides in this talk. Thank you.
Are there any questions or comments? Okay, let us thank the speaker again.